So, you are all here to learn about async landing iterators. Good. A landing async iterator is just a trait with a generic associated type item with a lifetime tk, and self that must outlive this lifetime. And a generic function pull next that takes 2 arguments, mutable reference to self that must be pinned, a context for the asynchronous things, and it returns a pull option of a self item tk. And that's it. So, questions? Okay, obviously I'm just kidding. Hello everyone, thank you for having me. I'm Edoardo Morandi. I'm a freelancer full stack developer. I'm an ex-bioinformatician and I fell in love with Rust in 1917. You can find me as Dodo Morandi, but I'm not a very social guy, so probably it's better to write me an email if you want to contact me. And stop talking about me, but well, landing async iterator really this time. Okay, in reverse, the iterator, you already know what an iterator is, okay? It's something that spits out an element one by one, okay? Simple. Async, it's generally related to concurrency in Rust, okay? And it's generally related to some sort of I/O, not necessary, but generally related to I/O. And you've probably already heard about async iterators because they're just another name for streams in the futures crate, okay? So async iterator, and then the missing part is just landing. The concept of landing is the thing that's been spit out from the iterator is actually partially or totally owned by the iterator itself. So it's not static, it's the user has been given something that must be given back to the iterator itself. In Rust, it's just dropping the thing because you have an lifetime inside and you just need to drop it in order to use again the iterator, okay? And this is the basic concept. And you could think that, okay, iterator, async, landing, but what about landing iterators, not async? They are a very known concept. They're interesting. They're mostly writable since the stabilization of generic associated types in Rust 65. And very interesting. I just find the async version more interesting. I think that you can build interesting, safe abstractions using landing async iterators, especially in resource-constrained environments, for instance, in bare metal. And they tend to push you to the limit of the language. And for this, I think they are pretty fun. So I decided to explore them with you. The landing concept. Let's try to analyze that in a better way. You have something A. Let's say that this A has a lifetime tick A, okay? We want to create this blue rectangle that takes not the ownership, but the borrowing of the A. So we have this blue rectangle with a lifetime tick A, mutable reference to A. Let's say that this blue rectangle has a method associated that wants to create another rectangle, a green rectangle. And this green rectangle must contain a reference to A, but it's given from the blue rectangle. And we are not consuming the blue rectangle. So what is going to happen is that we have a mutable reference to A, but the lifetime is tick B, when the tick B is the blue rectangle. Obviously, tick A must outlive tick B because A lives more than the blue box and the green box, rectangle, don't confuse it with box. And the interesting thing is that the green rectangle is not actually borrowed from the blue rectangle. It's lent because there's a borrowing of the mutable reference inside the blue rectangle, but it's inside. So it's kind of smart pointer, but it's not really a smart pointer. It's just something that is being lent to the user. And the interesting thing is that the borrowing thing just works as usual. So until you drop the blue rectangle, the green rectangle, you cannot build another rectangle, the red rectangle in this case, because there's just one mutable reference to a stack that can live at one point. So this is the brief idea of landing something. Let's see what the actual async iterator trait is. This is the trait stream, really, taken from the future script. You have an associated type item that is spit out from the pollNext function. This is very similar to the future trait if you look at how it's defined. Instead of poll, you have pollNext, and then you have self that is a pin mutable reference to self, a context that is just something that brings a state for the waker, something related to concurrency thing. And what is being returned is a poll, which can be ready or pending, that contains an option. Okay, you know what an option is, with the inside self item. Okay, this is concept of stream. It returns like an iterator something continuously, but it's based to work on async environment. The landing, sorry, we could just do that. The landing async iterator instead. Let's look at this. It's slightly different. You have a generic associated type. This is generic over a lifetime, which is different from the other one. And we have a bound self that must outlive TK. This means that the things that's been spit out must be dropped before the async iterator itself. The async iterator cannot be dropped before the thing that's been spit out, okay? Self must outlive the item, okay? Then, okay, we have a pollNext function, just like in the stream. This is generic as well. The lifetime in this case is explicit because we need to associate it to the lifetime of pin mutable self. And this is because the context is the same, really the same, but the output contains a poll, like before, option, but with the self item, lifetime TK. You see that the lifetime flows from the mutable self to the output, using obviously the generic associated type. So as you can see, it's not trivial, don't get me wrong, but it's not rocket science, okay? You can pretty understand what is going on with an if. You need to understand a bit about pin. I know that this can be rough, but let me just try to introduce you what pin is if you never heard about it. This is a library concept that is used to avoid that something can be moved, overridden, or in general invalidated, okay? And this has been defined in order to make the future abstraction sound. We are not going into details about this, but we are going to briefly get the basics of pin. This is just a wrapper type, okay? And this is a wrapper type for pointer-like types, not like in C. We're not talking about pointer thing with the asterisk, but something that points to something else. For instance, a mutable reference to T is a pointer-like type that points to T. Just it. Box, arc is the same. Okay? In Rust, pointer-like type is just something that generally implements deref and eventually deref mute. And the interesting thing is that you can unwrap the entire structure, so in order to get the pointer back, only if the target of the pointer is unpin. What is unpin? It's just an auto trait. So you have this auto trait. I don't know if you what an auto trait is. Send is an auto trait. Sync is an auto trait. Something that has been if something is an unpin in this case. If you have a container that contains only unpin things, then it's unpin as well. Because it's an auto trait, as in other case, you also have the negation of the auto trait. So you have not unpin. It's a double negation. Just remember that you need to unwrap the thing, and you can do that only if the target of the thing is unpin. If the target is not unpin, then you cannot unwrap the thing. So you cannot work with, for instance, if you have a mutable reference to t, it's pin, you cannot take the mutable reference, the t, if it's not unpin. Okay? Let's look at an example. We have two structures, A with a value i32, and B that is an instance of the struct B. As you can see, B has a value, okay, and it has this marker, a phantom pin marker. If something has a phantom pin, it's not unpin, because phantom pin, it's not unpin. Also, mostly all the features created by the async functions are not unpin. That's important to know. And what happens if you try to implement, for instance, future for A? In this case, A is self, okay? So you have this pin mutable reference to self. That means that you have a pin mutable reference to A, okay? And if you try to use the getMut function of pin, in theory you want to do that in order to get back the mutable reference to A. Unfortunately, this doesn't work, because, as said, A does not implement unpin because B does not implement unpin, and you have an auto trait. So the not unpin is propagated to A from B. So what can we do? We can use unsafe, unfortunately. So we promise not to override A. We must not invalidate A. And we can do using get and check mute on the pin. We get A, and then we can modify the internal values. We cannot modify B because it's unpin, and previously was undirectly pinned because it's a field of something pinned. But we can also modify value. If you try to modify B, override it, it's undefined behavior in practice. And OK, we just return the values. That works, but we are using unsafe. That's not the best solution. We have some tools around. We have the pin project crate and the pin project like crate that helps you to project the pinning from a structure to the inner fields. So how it works? You can just annotate the structures. As you can see, we annotated both A and B with the pin project. We also annotated the B fields as pin. So we promise that if the B is not unpin, that thing cannot be a mutable reference, but it must be pinned, okay, during a pin projection. Our implementation, we are implementing the poll as before, and we can use self-project, which is it's being created from the procedural macro or the declarative macro automatically. A, in this case, is a structure that contains mutable reference to the fields of A, or if it was pinned at and it cannot be unwrapped, it cannot be unpinned, it's a pinned mutable reference. In this case, for instance, we have a mutable reference to i32 and a pinned mutable reference to B. But we can use a.b.project as well, because we annotated B with pin project. And then we can modify the value. We return everything, and this is just safe Rust. So we can use the pin, the abstraction of pin without any kind of unsafe, just using some tools that have been provided for other contributor. And so we saw the trait. We saw how we can use pin in order to handle these situations. let's try to see how we can implement the landing async iterator for something useful. For instance, the TCP reader struct in Embassy without allocating. We want to use that in a bare metal situation if we can, and generally it's not the best solution to allocate, heap allocate in this situation. So what can we do now without the landing async iterators? Okay, it's pretty simple. We allocate a fixed array buffer, and in order to get the things, you can call read of the TCP reader in order to read into the buffer. What you get is the number of bytes read. If it's 0, okay, done. Otherwise, we can use the number to slice into the buffer, and then we can use the slice, sorry. And that's it. And then you go back to step 2. It's fine, it works, but you don't have any abstraction on this. It's just a loop. This doesn't scale very well because you need to do every time this kind of thing in order to read your bytes from the async thing in Embassy, and it's not the best. What can we do? We can do better. We want to try to create this abstraction, and we want to use a state machine. The first state is just the TCP reader and the buffer, okay? Nothing more. Now, the thing is, we want to call read on the TCP reader. Read takes a mutable reference, or I don't remember if it's a mutable reference or a constant reference, but it's the same, to the TCP reader, and a mutable reference to the buffer. So we have got this future that borrows from that. But we want to store this future inside the state machine. But we cannot do that at this point because it will be a self-referential type. And we cannot write that in safe Rust unless probably also using unsafe, you will get crazy to do that. What can we do? We can try, we want to play some tricks with the compiler. We need to respect the lifetimes. And so it's, we want to play some strategy. We can play Go. Not a programming language, the game, I mean. So we can try to detach the state from self, okay? So we just created the state and we try to detach it from self in order to detach the lifetime of these two from self. So we are not creating a self-referential type anymore, but we cannot leave that thing uninitialized. And for this, the strategy is to create a dummy state. It doesn't mean anything. It's a state that is just there to avoid uninitialized memory. And at this point, we have this future that returns a number, which is the number of bytes of the buffer and the TCP reader. Okay, but we cannot drop that. We need the TCP reader and the buffer. So we can use the fact that creating async blocks automatically is able to create self-referential types. So if we encapsulate the call inside an async block, we can then return the buffer, the TCP reader, and the number of bytes read. And at this point, we have a future that can be stored inside the state. And we have our third state of the machine. At this point, it's simple. We have the future. We can just pull it. Simple. Obviously, you take the result back. You have the number of bytes. You take the TCP reader and the buffer. You rewrite them into the first state. And then you can just slice the buffer, land the slice outside to the user. It's not trivial. Don't get me wrong, okay? There's some kind of little things that also require unstable. I'm not going to talk now about this. If you want, we have some slides about this and bonus slides in the end of the talk. But the concept is that it's possible to do that. Not easy, not trivial, but it's possible. So we really built an abstraction without allocating for bare metal things that can leverage the fact that we can stream from a TCP reader. this is nice, I think. So we saw the trait. We implemented it. We also saw how it works with pin. Let's try to use this landing async iterator. OK, we implemented it, but we are not actually using it at the moment. You probably, maybe you used sometime the next function from an iterator. Yeah, you can do that. Generally, you want something for each, filter, map, and so on. And this is the same for future and the stream trait. Because using just the bare minimum methods, it's not the best developer experience, you know. And so it's possible to use additional methods. And it's possible to define them. As you can see in the iterator itself, the trait, they're defined inside the iterator. Or for instance, with the future and stream, you have extension traits that can define auxiliary method for them, and they're very useful. So we can try to implement them as well for landing async iterator. We are going to implement just a couple of them. We don't have much time, unfortunately. One interesting thing before we start. There are emerging properties from the landing async iterator. You cannot store anywhere your length thing, because, as we said before, you must give back the length thing to the iterator. You just need to drop it before using the next function again. So you cannot really implement something collect, last, min, max. There are a lot of auxiliary methods that are not possible. They're not, if you try to implement them using unsafe, the implementation will be unsound by definition of the trait. So this is an interesting emerging property. But let's try to implement something, OK? Let's start with for each, because for each is pretty simple. We have this function that takes a closure, OK? The closure just takes the reference, the self item. We need a higher rank trait bound, the 40A right there, because we don't actually have a lifetime inside the definition of the function, because when you do the poll next, you have the iterator, and what you got back, it's something with a lifetime, but you don't have a lifetime before, so this is a higher rank trait bound. And we don't need to return anything, so it's pretty simple. In this case, I'm showing you how we can do that using a structure. If you want, we can talk about other possibilities later. And this is a structure. Remember pin project before? We're using it, and we say that the async iter can be pin, probably it's going to be pin, and we have the function. So this is some boilerplate. OK, we want to implement future, because you probably want to write down something like async iter dot for each dot await, because it could be very useful to do that. The output is nothing, the unit type, and we can try to implement poll at this point. This is the simple implementation of poll. Let's try to analyze it. We are going to use the self-project method, just like before, OK? So this is going to, oh, come on. What is going on? OK. This is a structure, as before, with a mutable reference to f and a pinned mutable reference to the async iter. So we can use asMute, which is a method of a pin that makes us able to use the pin more than once. Otherwise, we would consume the pin mutable reference. And we are in a loop, so we want to do that. And then we can use the poll next function, because we define the poll next function, OK? At this point, we can just use the task-ready macro from the standard library, which returns something only if the poll returns ready. And then we can just loop until when we get some element. Inside the loop, we have the function from this f, and we just pass the element to the function. And nothing more, because when we finished, when we don't have any more element, we just return already with nothing. And this is all we have to do to define the for each. This is not bad, really. If you follow me, I think you could grasp the idea of pin projecting. And okay, you need to understand that you need to call as mute on pin, but it's not so hard, okay? It's not rocket science, even in this case. Let's try to implement something different. The filter. Okay, bear with me, because it looks simple, okay? We are just defining something similar. Our closure just take a mutable reference to self, because we want to filter, so we have a reference, and the closure must return true or false, depending on the fact that we want to filter the element itself. We return the structure, an auxiliary function, a structure as before. This time, this is the filter structure, pin projecting, anything new for now. This time, however, we want to implement a landing async iterator for the filter, because we are going to land something from the inner async iterator, okay? The item, in this case, is simply the item of the underlying landing async iterator, and this is how we can write the poll next function. So, projecting, again, we got this that is a structure with a mutable reference and pin mutable reference. We need to use as mute on the async iter. We are in a loop. We pull next. We task ready for the next element when it's ready, and then we loop until we have some element. Then we take a reference to the element and try to send it to the predicate. If we've given true, then we return already some element, because it's not. It's okay. It's true. We must return the element. When we finish, we return already none, because the stream just finished. It should work, right? Do you think it should work? No. And this is a strange error, because cannot borrow the async iter as mutable more than once at a time. Wait. Okay, this is a full error, but this doesn't make any sense, because, okay, this is what we wrote, okay? And we have element that is given out from the poll next function, okay? We get some element, we have element, we take the reference and give it to the predicate. It's okay, we have a Boolean left. And then, in this case, if it's true, we return the element. So we are not looping again. Otherwise, we are dropping the element. We are not using the element more than once, for more than a loop. What is going on here? Oh, the borrow checker is just wrong in this case. I'm sorry. We need the next generation borrow checker, Polonius. And you can try to activate it using Rust flags, passing .z Polonius. And this is probably going to be necessary in order to implement our filter function. So, okay, we use Polonius and it works. Oh no, what is going on again? Cannot return value referencing local data, but we don't have local data inside. Element is a local data, but it doesn't make any sense. It belongs to the inner iterator. Okay, maybe the fault is about this little thing. This is the definition, the signature of the asmute function inside pin, okay? As you can see, self in this case is the pin, not the inner type, okay? So we take the mutable reference to the pin, and we return a pin with a mutable reference of the target. Maybe it's better to look at an example. We have the simple function, okay? It's a test, it's a generic over T because we don't care about the type. And we have this A that is a pin mutable reference to T. And we explicitly define the tick T lifetime, okay? And we just try to define B using A as mute, okay? A has an intrinsic lifetime, obviously, like anything. We just define it as tk because it's simple. Remember that tick t must outlive tk because it's tick t is something elsewhere, not here, in another castle. A as mute can be seen as pin colon as mute and the self, but self is a mutable reference to A with tick A, not tick T. And the definition means that our lifetime flows from the mutable reference to self to the mutable reference to the target pinned. So it means that B, it's a pin mutable reference T with lifetime tick A, not tick T, which was the original lifetime. This also means that if you try to return return B, you get an error because this is a local value. But okay, you're saying, but that's not how mutable reference works. They just work. If you try to take a mutable reference to T and you use multiple times a function that consumes that mutable reference to T, it works. Mutable reference to something is not copy, but you can do it anyway. And if you try to reborrow A with B and return it, it works because the compiler is magic. And a mutable reference to something is special, has a special treatment. We have lifetime ergonomics in this case. But pin is not special. We don't have that for pin unless we have this thing stabilized. The pin ergonomics is an incomplete feature. It has been improved during my presentation, when I wrote the presentation, but things are going on and things are improving, but for now, things are still unstable. In this way, you could just omit as mute and things would have worked. Probably we're going to get this, maybe, but let's go back to our implementation. We were implementing filter, remember? Okay, and what can we do at the moment? We can just use unsafe. In this case, it's possible. So we just split the predicate and the async iter because it's better to do that. We can just use get unchecked mute, and we promise not to override the async iter, and we promise to use the async iter pin again later. We just need to remember that, okay? And so at this point, we can just rewrite our implementation using the pin, the unsafe pin new unchecked that takes, and this is the magic, the reborrowed version of async iter. So this is tricky. Okay, I really understand it, but it's slightly possible to try this. So even with filter, I tested it. Because you need to test this, otherwise it would be very scary. And it works. Mirit approves. The problem is that you really need to understand what you're doing if you try to write this, because it's very easy to shoot in your foot. Also, it still requires Polonius. Our unsafe does not escape from that problem. And unfortunately, time's out, guys. I'm sorry, we only have time for those two implementation of this, but there are a lot more, and you can try. So, we just see a brief idea of how landing async iterators are. They are very powerful abstraction, and I think that it can be defined as a bleeding edge abstraction because you really need something that you generally don't want to touch. And the idea is we are just exploring something in the Rust ecosystem, okay? This is not something that you want to do in production, okay? Please don't take this thing and put it in production. That's not a good idea. But the point is that there's something to explore out there. As Tim said previously, Rust needs to improve in a lot of ways, and the thing is that sometimes, if you have time, it can be very fun to do this kind of exploration. Remember to reason with the compiler and not fight against it, because you need to have fun doing this, okay? And even if the compiler is wrong, you need to try and understand what is going on and not try to fight it. Keep your exploration fun. And obviously, there are lots of things that are worse than I show you. There are lots of dark corners about these whole things. Lots of strange error, lots of compilers stuck doing nothing, but it was compiling just 2 lines ago. I don't know. But it can be fun. I had fun doing this. I hope you had fun with me. And I just want to thank you. If you want, there's a repo with some code, exploration code. The main branch contains what I've been able to make it compile. There's another branch that if you try to check out different commits, you will see my desperation at some point, but that's it.
Are there any questions? I'll give you the microphone. You answer it. Yes?
Is it working? Okay. Just out of curiosity, the limitation where we need to use Polonius, in the final solution we are already using async. What about transmuting and using a compatible lifetime just to use the standard compiler, the stable compiler?
Yeah, you can do that. The problem at that point is that you're really on your own, and the fact that sometimes it's pretty difficult to understand if you're right or wrong about some assumption. You can transmute that. You actually not need to, in certain situations, to transmute your thing. Sometimes you just need to cast it to a pointer and get the reference back, and you transmuted only the lifetime at that point. But sometimes you really to use transmute. With that, you can do that. At that point, it should work. I'm not sure if the model, the stacked borrow model in the stable Rust C will be okay, but it's probably okay. I could see. So that's a good question. Thank you.
Okay. Any other question? So shy. Okay. Oh, I didn't see it.
You mentioned that the async closures bring in some more fun.
Yes.
Have you tried implementing a lending async iterator async fn in the trait?
Oh, yes. But unfortunately, you cannot get back the type of the future of an async closure for now. And I tried also to use the return type notation for that, but if you try, it just say this is still not supported for now. It's always things about the future. And that's a very good point, because initially I just thought that I could write at least one single auxiliary function using async closure, but I've not been able to do that, unfortunately. But nice question indeed.
Any other question? Yes.
Do we have? Oh, okay.
Thank you for the talk. I have a question about the proc marker that you use for the pin, where you said there's some stuff missing still. So it was not quite clear to me how integral that is for the implementation without unsafe, and how whether the crate needs to be externally loaded or.
I'm sorry, I just lost you at a certain point. You asked if the pin project crate uses unsafe behind the scenes.
You said you needed this crate to not have the unsafe in your code.
Oh, yes.
And then is it then implemented like that in the crate, or? Yes, yeah.
The crate uses some kind of assumption and tricks, thanks to the fact that it's a macro, in order to guarantee that you cannot just escape the invariance needed to about the pin guarantees. In practice, there's some kind of tricks related to the drop, because our actual drop doesn't actually need the pin mutable self, and they had to do some tricky things, because in theory, if I recall it correctly, you could just have a manual drop implementation bogus that could cause undefined behavior, and then they made some tricks to avoid that. Probably you will need to check what they are actually doing, because I just recall how it works, but I'm not very prepared how they internally do the things. But these are mostly the main important thing. The drop thing is pretty interesting. Oh, if you're interested, the light version, the pin project light version, it's a declarative macro, and it's pretty powerful. But generally, there are some limitations related to enums, if I recall it correctly. No, not enums. Sorry, the tuple struct likes. So because you're not actually able to do the .0, .1 inside a declarative macro. It's kind of hard to do that for now. I hope I reply your question.
Okay. Any other question? Yes.
Hi. Thank you. Great talk.
Nice.
I've been wondering about path to stabilization. Now the Rust 2024 edition is around the corner. I'm sure this one won't make it. Is that something that can only be stabilized in the Rust 2027 edition, or is that something that we can kind of stabilize and land before?
Oh, in the 2027? Okay, probably lots of things. I cannot, I'm definitely not official. I just can hypothesize what is going on. The thing is that, for instance, the type alias import trait is very useful to do a lot of things related to all of these. In particular, the implementation for Embassy requires this specific unsables feature, because you need to name the opaque feature, and This is probably going to be stabilized next year. So we really hope to have it in the 2027 edition. And other things, it's difficult to understand what is going on because, for instance, the return type notation is going to be stabilized, but I'm not sure if they think that they're able to get a fully feature complete thing for the 2027. And for instance, the what was the name? The associated type import trait, if I recall it correctly, is started. They thought they could be stabilized next year, but the development stopped. So I don't know. There are lots of things. Polonius, they're going to probably stabilize at least part of Polonius. The funny thing is, yesterday, when I was trying to implement something more for the landing async iterator, I also been able to break Polonius. So things are going to be better, probably not perfect even for the 2027 edition.
Thank you.